Imagine stretching a rubber band, it snaps back no matter how many times you pull it. That's the essence of a hyperelastic material. It can stretch to several times its original length and still return to its shape, again and again. Unlike metal springs, which deform permanently if overstretched, hyperelastic materials handle huge deformations with ease. This isn't just simple elasticity. The hyper means their stretchiness is complex and non-linear. For hyperelastic materials, the relationship between force and stretch isn't a straight line, it's a curve. A small pull might stretch it a lot, but more force is needed for further stretching. This unique, non-linear behavior is what makes them so useful and fascinating. The secret lies in their structure, long, tangled polymer chains, like a bowl of spaghetti. When stretched, these chains uncoil, allowing for massive deformation. Cross-links between chains act like anchors, snapping everything back when the force is released. This lets them store and release energy efficiently, like winding and unwinding a molecular spring. That's why they're found in nature, think skin and muscles, and why engineers are using them to build the next generation of machines. Hyperelastic materials are the foundation for soft, adaptable robotics. They're opening up new possibilities for machines that move and interact with the world in ways we once only imagined. Traditional robots are rigid, powerful, and often dangerous. Great for factories, but not for delicate tasks. Soft robotics flips this idea, asking, what if robots were soft, safe, and adaptable, like living things? Hyperelastic materials make this possible, letting robots bend, twist, and stretch without breaking. They're perfect for building actuators that move like muscles, not motors. This means soft robots can grip fragile objects or interact safely with humans. If a soft robotic arm hits an obstacle, it bends around it instead of causing damage. This adaptability is crucial for robots working in unpredictable environments. Soft robots can perform complex motions with simple, flexible structures, sometimes just a single inflatable part. The material itself helps compute movement, reducing the need for complicated controls. This is called morphological computation. The robot's body does part of the thinking. Hyperelastic materials are the key to making robots that are safe, gentle, and smart by design. Engineers have a toolkit of hyperelastic materials, each with unique strengths. Silicones are the most versatile, stable, water-resistant, and easy to shape, perfect for rapid prototyping. Natural and synthetic rubbers are tough and elastic, ideal for robots that need to withstand repeated stress. Synthetic rubbers like neoprene resist oils and chemicals, making them great for harsh environments. Hydrogels are soft, water-rich and biocompatible, excellent for medical robots or artificial tissues. Some hydrogels even change shape in response to temperature or light, enabling smart actuators. Each material, silicone, rubber, hydrogel, offers a different balance of strength, flexibility and function. The choice shapes how a robot moves, where it can work and how long it lasts. New composites are being developed, promising even more exciting possibilities for soft robotics. To design a soft robot, engineers need precise data on how materials behave, not just that they're stretchy. Material characterization starts with tests like the uniaxial tensile test. Stretch a sample, measure force and elongation, and plot the stress-strain curve. For hyperelastic materials, this curve is non-linear, a unique fingerprint showing how the material stretches and absorbs energy. Engineers use this data to predict how a robot part will deform under load, but real robots face complex forces, so scientists also run biaxial and planar tension tests, stretching materials in multiple directions. These tests build a complete picture of material behavior. Published data from these experiments lets others simulate and design with confidence. Without this foundational testing, soft robotics would be guesswork. Careful lab work, stretching, squashing, twisting underpins every soft robot design. It's the bridge from material science to real-world machines. With experimental data in hand, engineers turn to computer simulation, specifically the finite element method, FEM. FEM breaks a complex object into thousands of tiny elements, each governed by equations describing its behavior. For hyperelastic materials, engineers use advanced models, like Neo-Hookean or Mooney-Rivlin, to match the non-linear stress-strain data. The simulation applies virtual forces, predicting how each element deforms and how the whole object changes shape. This lets engineers see how a robotic finger will curl, where stress concentrates, and if the material might tear. FEM enables rapid virtual prototyping, tweaking designs, materials and shapes before building anything physical. It saves time, money and materials, allowing for more complex, optimized robots. The process transforms how soft robots are designed, making innovation faster and smarter. FEM is the essential link between lab data and real moving machines. It's how we turn squishy materials into functional, reliable robots. The power of hyperelastic materials is clear in real soft robots. The Octobot from Harvard is a fully soft, 3D printed robot powered by chemical reactions that inflate its tentacles. No rigid parts at all. Soft robotic grippers, inspired by starfish, use silicone fingers filled with coffee grounds. They gently wrap around objects, then stiffen with a vacuum for a secure grip. In medicine, soft silicone sleeves help weak hearts beat by gently compressing and twisting in sync with the heart's rhythm. Snake-like robots made from inflatable silicone segments can crawl, squeeze and climb through tight spaces, adapting to their environment. These machines show how hyperelastic materials enable safe, adaptable and innovative designs. They move not with brute force, but with flexibility and intelligence built into their very form. Soft robotics is redefining what machines can do, thanks to the magic of these materials. Picking the right hyperelastic material is a balancing act. There's no one-size-fits-all. Mechanical performance matters. Tough synthetic rubbers are best for high-force, long-life robots. Silicones excel at complex shapes and easy fabrication. The environment is key. Industrial robots need oil and heat-resistant rubbers. Medical robots require biocompatible silicones or hydrogels. Hydrogels are perfect for tissue-like softness and medical use, but can be tricky to handle. Cost and manufacturing ease also play a role. Silicones are cheap and simple to process, while some rubbers need expensive equipment. Sometimes the function dictates the material. Smart actuators use stimulus-responsive hydrogels. Transparent robots need clear silicones or gels. Engineers weigh strength, flexibility, resistance, cost, and function to make the best choice. Material selection is at the heart of creative engineering in soft robotics. The right choice shapes not just how a robot moves, but what it can achieve. It's a core part of what makes this field so dynamic and innovative. The future of robotics is soft, safe, and collaborative, made possible by hyperelastic materials. Understanding these materials isn't just academic, it's the key to next-generation machines that work alongside us. The same tools used for soft robots can improve medical implants, wearable tech and prosthetics. This field blends engineering, chemistry, biology and computer science, demanding new ways of thinking. The challenges are big: stronger, smarter, self-healing materials. But the rewards are bigger. We're building machines that are intelligent not just in code, but in their very form. Soft robotics is about creating technology that adapts to our world, interacts safely, and solves real problems. The future won't be built from steel, but from soft, complex materials that let machines bend without breaking.